Okay, so now we will generate clusters in 2D. So, uh, okay, so let's see. Okay, set seed is a command using which you can set the seed from which the random number will be generated. So it could possibly be that I'm running this program right now, so my generated random number could differ to your generated random number when you will be running the same code in your machine. So to make a harmony between the program which is running right now and the program that you might run, this set seed thing is being introduced so that the numbers which will be generated to your machine will be surely random, but will be the same as the number that are generated into the my machine right now. So if you want to look the same output, don't forget to write this command set seed and give the seed value 1 2 3 4. So now we will generate the random x variable. It's not our previous R norm commands. There are certain things are different than our previous R norm command. And, over there, we have specified our mean as one static value, but over here our mean is itself the vector of 12. So this thing. This part, if you observe it, it is REP stands for repeat. So what does it do? It repeats each and every number inside this vector. How many times? 4 times. Okay, so each keywords describe how many times this number is going to be repeated. So it gives basically vector of 12. Each element of this vector is repeated 4 times. So 4 times 1, 4 times 3, 4 times 5, and standard deviation would be 0.2. So our norm gives us basically the value of x which has the 4 x value for which mean is 1 and standard deviation is 0.2, mean is 3 and standard deviation is 0.2, and mean is 5 and standard deviation is 0.2. So the same goes for r. So if we generate those two numbers and if we plot them, so okay, as you can see, they look something like that. So from the visual analysis, we can see that okay, it seems like there are 3 clusters around there. So now we will use the k-means algorithm inside R to identify that how many clusters are there. So for that we have to make the data frame combining those two vectors that we have generated. So this is the command from which we can make data frame of those two vectors x and y that we have generated. I'm going to name it as df. Then I'll run k-means and store the result into a variable called kmc. If you can see that the center I have specified 3 because my visual analysis says that okay, there could be 3 centers. You can see it's a toy example. There are clear boundary. In the normal example, our attributes normally won't be a single attribute. Okay, so the attributes could be multiple, and you can't maybe you cannot find a single boundary around, but from the intuition also you can specify how many number of clusters could form at the end of the algorithm. So the KMC gives us number of clusters, various information regarding clusters, but it actually acts as a data frame of which the cluster attribute gives us the cluster label associated with each and every data point x and y. So now we are going to combine this cluster vector with our existing data frame, So okay, so let's see. So our data frame looks something like this. So previously data frame had uh, two attributes x and y. Now the cluster itself is uh, as a we have combined it as a part of this data frame. Okay, so now we are going to plot it. Okay, so these are the command to which we can plot. So here you can see that I have given each and every cluster at different levels. So the k-means has identified this area as one cluster, this area as one cluster, and this area as one cluster. It's blue, green, and red color. Okay, fine. So, if you have remember, we have used a data set called Iris when we have discussed about frames. So now we are going to use that data set again, and we will use the same k-means clustering algorithm, okay, on that Iris. So first of all, we will load the Iris data. Then we are going to take only 1 to 4 column, because the fifth column itself is a label. So we want an unlabeled data set. So Iris test will have each and every data of Iris data set except that fifth column, which has the category of flower. So now I'm using the k-means algorithm, and here also I can for now I know that okay, there are basically 3 categories, but this value you should you can get the estimate of what value you should put over here by kind of your experience, or this roughly scan of the data which you have. So now okay, we'll see that what do we have. So now we are plotting the result. So this is the result. This is the actually okay. This one is the actual result of the Iris data set. So here we can see that the columns has assigned, each and every columns has assigned a separate color. So initially they are black. Then if the species is Setosa, then blue. If it is Virginica, then red. Versicolor remains will be automatically will be colored as black. So okay, so this over here you can see that this is the actual distribution. Now if you are new to this kind of plot, okay, this is known as a scatter plot. So let me show you what does it mean. So this over here in this square, you can see it represents each and every dimension. This square, you can consider that if we draw an XY plot with X as this dimension and Y as this dimension, so we will get this plot. Okay. Same goes for this. If we will have Y as a sepal length and X as a petal length, then we will have this kind of plot. All right. So this is basically a scatter plot. Over here you can see the now a sepal length as and petal length. They are inverted over here. So now petal length is working as y-axis and sepal length working as x-axis. So the same visual effect that the same graph that you are looking over here is kind of inverted over here. Okay, so this is the scatter plot basically, so that you can match each and every attribute pair inside your data set. So over here you can see that the black colored, red colored, and blue colored classes are there. So these classes, this is showing that these classes are kind of different from each other. Okay, and over here you can see that this is a species column. So in this column, each and every class is separately explained. So you can see that there are clear line. This line basically shows that it belongs from one class. Same goes for this vertical lines. So now we will use the k-means algorithm on the data set which is unlabeled. So, we have already applied that k-means, and now we will color our data point according to the cluster label that we got from that k-means algorithm. So now we are going to color it blue, red, and green instead of blue, red, and black. So this is the new pair graph that we are getting. Okay, the syntax of pair graph, you can see this is the syntax. So you can pass the argument, the data frame for which you want to draw a paragraph, and this is COL actually represent the color profile of your paragraph, which we have distinguished blue, red, and green, and PCH defines your data points are filled or empty. So if you remember in our previous graph, we have seen that the data points were like empty circles, but here they are solid circles. So that thing we can control by this PCH variable. So here, if you observe, now, so we have this red class. For now, we don't know that which class is this, whether it is Satosa, Versicolor, or Virginica. We don't know that. But for us, we can see that okay, this red class is basically separable. We can in each and every pairwise graph, we can see a separate linear separation of this red among those two. So for the k-means, it naturally it would be easy to identify which which data point is belongs to this red color graph. The confusion arises between this thing. So the blue and green basically kind of hugely mixed up. So for k-means, it's really challenging to identify the correct point. Now here you can see the point over this line. So this is actually all point over here should be of blue color. As we have seen in the previous graph that all point in this part of the graph and in the same line will have same color, but here these points are not. So we can consider that okay, so these are basically the errors made by the k-means algorithm. Okay, so this vectors, and this is the blue point that should be over here, but it came here. So these are basically an error points that were due to the they were made by k-means algorithm. So apart from this pair graph, we have pair.panels graph. Now pair.panels is extended version of pair graph, and so if we it gives us an error that okay, it cannot find pair.panels is just because that I haven't included the library in which they belong. So PSYCH is the library. Please do install this library and include it in your program. Okay, so now I hope that my paragraph will run. Okay, so Okay, this is the pairs.panels graph. Okay, these graph sort of look like the pairs graph that we have seen before, but it gives us some very huge and some more information apart from that only pair graphs. Okay, so pair.panel, what does information it gives? So here these diagonal elements are again these are dimension name. Okay, apart from the dimension name, they gives us the distribution of the values that those dimension are having. So here we can see that okay, it's roughly having the normal kind of distribution, and it's definitely this thing is not a normal, or this thing is some other curve. So we can at least estimate that okay, which curve we should estimate when we are kind of estimating this the value or the parameter that belongs to this dimension. All right, so okay, it shows some other information. It's like now this is showing the correlation. These are the correlation number. So the correlation between let's say sepal length and petal length is 0.87, so which is a fairly high amount of correlation, and visually that thing you can realize by looking at the intersection. So this is sepal length and petal length. So this is their intersection. So over here you can realize this is the ellipse, and this is basically the top view of the 2D Gaussian that they make together. So petal length and sepal length, both when they make 2D Gaussian, it looks something like that. So if you have remember, this was discussed in a class that if the 2D Gaussian is somewhat inclined towards the axis, it's neither straight or let's see, nor properly aligned with x-axis nor aligned with y-axis, then it seems like the value in the 2D Gaussians are fairly correlated. In that case, the covariance matrix will not be something like value 1, then 0, then 0, and then value 2. So it will not be. The anti-diagonal also will have a certain value. So you can guess or you can estimate from here. So this seems like less correlated. Let's see that what sepal width and petal width. So petal width and sepal width. See, compared to sepal length and petal length, the sepal width and petal width are less correlated. We can infer from the graphical information that we have provided as well as the numerical information. Okay, just note this thing that here the categories of data are not color coded. They all are plotted as black color. Okay.